All right, so our last pericyclic reaction that we're going to talk about are the sigmatropic reactions. This is our last category here, and we notice that what's characterizes a sigmatropic reaction is that there's no change in the number of pi bonds and no change in the number of sigma bonds. We're still going to see this concerted circular motion of electrons, but the net effect is not going to be any change in the number of bonds that occurs. Like our electrocyclic reactions, our sigmatropic reactions are intramolecular rearrangements, right? So you're only going to start out with one substrate that's sort of reacting with itself. So what is occurring exactly? Our rules as to where the base of our arrow is and where the head of our arrow is going to change a little bit here. Okay, so for the other two types of pericyclic reactions, you can't go wrong as long as the base of your arrow starts at a pi electron and the tip of your arrow is at an sp2 electron. That's not going to be the case here because we're actually going to be breaking a sigma bond, but you can start out that way. And that's what I recommend you guys do to make sure that you're not falling into any sort of a trap. You're going to start with the tip of your arrow at a pi bond and the head of your arrow at an sp2 hybridized carbon. But from here, you're just going to make sure that all your electrons move in a circular fashion, okay? So we got the one, base of our arrow starts at a pi bond, the head of our arrow at an sp2 hybridized carbon. Now when we make our second jump, notice that it's going to be, the head of our arrow is now an sp3 hybridized carbon. And I got to continue this circular motion of electrons. So that's how I go about breaking this sigma bond here, okay? So what is what? So this pair of electrons that was in that sigma bond now forms this pi bond. This jump here is how I formed my new sigma bond here. And then this pair of electrons, this jump here is how I have this pi bond moved. Okay, so notice that I haven't had a net change in the number of sigma bonds and pi bonds, but I have moved them around. And in particular, I've broken a sigma bond on the one side and formed a sigma bond on the product side, okay? So in this particular example, you could see that this is the bond that's broken. I can tell that because the base of my arrow starts at that bond, and this is the bond that's formed over here, and that's formed by this arrow, okay? These are called, well, there's a few different sigmatropic reactions. The ones that we're going to learn about are going to be 3-3 sigmatropic reactions. And why do they call it that? Well, this is the transition state right here, right? Where these dotted lines represent the movement of electrons, either bonds that are being broken or formed. And again, just like all of our pericyclic reactions, they have a cyclic transition state. That was one of the key things that unify all three of these. So why is it called a 3-3? Well, if you look on the one half of your transition state, there are 3 carbons. And if you look on the other half of the transition state, there are also 3 carbons. So there are other types of sigmatropic reactions that aren't 3-3, but these are the ones that we're going to focus on today. In particular, there's 2 sort of special names for them. The first is called a cope arrangement. And this is a 3-3 sigmatropic rearrangement where all 6 of the atoms in that transition state are carbon atoms. Okay, so how do you spot whether or not a cope rearrangement can take place? Well, I have to have 6 atoms that can be arranged in a ring, and the spacing of the double bonds is really crucial, right? So they have to be 1, 2, 3, 4, 5, 6. So this would be any 1,5-alkene. Let's put that up here, 1,5-alkene. And that doesn't necessarily mean that it has to be at the tip. You know, the first pi bond has to be at the very end. It could be internal. This is just referring to the spacing of these pi bonds. So let's take another example, something, and I'm going to draw it in this straight chain format, something big and long, where we have the pi electron, where we have our first double bond here. Well, if this is going to be able to undergo a cope arrangement, the other double bond has to be located 1, 2, 3, 4, 5 carbons away. Okay, so this example here would be another molecule that could undergo a cope rearrangement. It's all about the spacing of those double bonds, right? They have to be located 5 carbons apart using that proper counting where we locate the position of a double bond by the first carbon, right? So if we were being, I guess we can go through and name it just to be really, really good. 1, 2, 3. Let's make it a decade. This would be 3, 7 decadiene. Okay, and again, because those double bonds are located 5 carbons apart, this could also potentially undergo a cope rearrangement. So let's see. First of all, how do we do this mechanism? The first arrow you're going to draw follows the same rules as all of our other ones. You start at a pi bond and connect to an sp2 hybridized carbon, but then from there, you're just going to make sure everything goes in a circle. So this goes there, and now I break my sigma bond in this jump here. Okay, and then so this would be the product of this particular cope rearrangement. This would be an example of a cope rearrangement that actually favors the products. So why would that be, right? You could catalyze back and forth. I could do the exact same thing in the opposite direction here, right? That would also be a cope rearrangement. Why is it then that this particular one favors the products? Because notice that here you have a more this double bond here is more highly substituted, right? So it forms a more stable compound by forming a more highly substituted alkene. The other rearrangement that we're going to talk about is a Claisen rearrangement. So remember the cope rearrangement, all 6 members in that transition state had to be carbon. A cope rearrangement has an oxygen in there. So, a Claisen rearrangement has an oxygen in there. Very similar to a cope rearrangement in the sense that our double bonds are again located 1, 2, 3, 4, 5 carbons apart. Importantly though, there's an oxygen in there. These occur when you have a allylic vanillic ether. So what the crap does that? Well, let's just remember that when we have an alkene, let's draw a random alkene here. These positions are called the vinyl positions, the vinyl carbons. And these positions here are called the allylic carbons. So an allylic vanillic ether is an ether where one half of it is an allylic group, and the other half of it is a vanillic group, or has that oxygen bound to a vanillic carbon. And why these, what's so special about these allylic vanillic ethers is that gives you that perfect 1-5 spacing of the double bonds. And so we can see the same thing. How am I going to draw this mechanism here? First arrow, I'm going to make sure the base of it is a pi electron and the tip of it is an sp2 hybridized carbon. And then I'm going to just make sure everything goes in a circle from there. So this would go here, and then this is the breaking of that single bond. Okay, so notice that what happens if we have a allylic vanillic ether is it'll rearrange itself into an aldehyde or potentially a ketone, depending on aldehyde. Sorry, it's hard for me to spell when I'm talking. An aldehyde or a ketone, depending on what else is going on. If there was a group here, it would be a ketone. Okay. There is, and so real quick, just to hammer home, how do we know that our molecule will undergo a sigmatropic rearrangement, or in these 2 cases that we've seen, the cope rearrangement or the Claisen rearrangement? The key there is it's going to be an intramolecular reaction, but I have double bonds that have that special 1-5 spacing. One very specific example of a Claisen rearrangement will also occur with an allylic aryl ether. And I wanted to do this one because I think that it's potentially going to be in your Wiley Plus homework. The sigmatropic rearrangement, nothing sort of special goes along here. How do I make sure that I do it correctly? I'm going to put the base of my arrow where? And the tip of my arrow where? Base of the arrow at a pi bond, tip of the arrow at that sp2 hybridized carbon. And then from there, just make sure everything goes in a circle. And then the last one will be the breaking of that sigma bond. So that would get me to this compound here. Okay, but now this will undergo, because just by nature of it starting out with this aryl group, this can undergo a special type of intramolecular rearrangement we call a tautomerization. So remember we talked about this. This is a keto-enol tautomerization. We first sort of talked about it in chapter 9. We'll talk about it again when we talk about aldehydes and ketones, but just to point you guys in the right direction if you want to see what's going on here. This would be from chapter 9, slides 42 and 46 in particular. They can be either acid catalyzed or base catalyzed. So those are those two slides. The bottom line is ketones can rearrange into enols. Enols can rearrange into ketones. Usually this equilibrium actually favors the ketone. That's what we've seen it before. However, in this particular case, this tautomerization will favor the enol, right? And an enol is when you have a double bond directly next to an alcohol group. So this is my ketone. This is my enol. This is this keto-enol tautomerization. The reason why this particular reaction actually favors the enol is because you get this nice stable benzene ring that's formed. Okay, so this is a very specific example using an allylic aryl ether, which will actually first do our normal sigmatropic rearrangement forming a ketone, but then another step further will undergo this intramolecular tautomerization to finally end up with an enol.